Hello students. In this lesson we're going to optimize the dimensions of a poster. So we're going to find the dimensions of a poster that have the smallest area. And contained within this poster there's some printed material. And you can see that's going to actually give us one of our constraints. So the tricky part of this problem is that the top and bottom have margins and they're of different sizes. So we're going to have to figure out a way to work around that and then get the dimensions of the poster. So remember, at the end of the problem, we're actually going to have to add those margins back in to our final results. All right, so this problem has a lot of good calculus and algebra involved with it, so let's dive in and get started. Okay, so the first thing we'll do here is draw a picture. And you can see here we have the printed material in the center, and that'll have dimensions x for the width of the printed material and y for the length of the printed material. Now we're going to have to, we're going to find x and y, what those are, but when we do, we're going to have to add in the margins. And so at the top and the bottom we have 8 centimeters, as you can see here, and on the sides we have 6 centimeters here and here. All right, so the left side of the poster would be y, and then you have to add 8 for the top and 8 for the bottom. And then the width is going to be x here, and then you have to add 6 for this side on the left and 6 for this side on the right. And we're told that the area of the printed material of the poster is 388 square centimeters, so x times y is 388. Okay, so let's take some time to combine the y plus 8 plus 8, and that'll give us y plus 16. Then the x plus 6 plus 6 will give us x plus 12. And now we have a way to determine the area of the entire poster, given the dimensions x plus 12 and y plus 16. So we'll set up our objectives and our constraints. So remember, our constraints will generally include some kind of statement like x and y are greater than 0. One constraint, we're told, is that the printed material on the poster is fixed at 388 square centimeters. Okay, we don't have a choice in that. We're constrained by that result. And then we're told we have to minimize the area. And the area of the poster is going to be x plus 12 and y plus 16. So we'll FOIL that out. X times y is xy, 12y, 16x, and then 12 times 16 is 192. Now we know x times y. X times y is 388. So we're going to take that and substitute that into there. Okay, so let's see. Let's just do that. There we go. And I'll just put that on the next line. So 388 plus 192 is 580. Then we have plus 12y plus 16x. Just bring those down there. So that's the area we're going to minimize. Now, this is a function of two variables, y and x. We want to turn that into a function of one variable. So we're going to take y, and we solve for y by dividing both sides by x. And that's okay to divide by x because x is greater than 0. And we're going to substitute that 388 over x in for y. So let's move that over there, and I'll just rewrite that down here. And then 12 times 388 is 4656. And so our area function now is just a function of one variable, x. So a of x is the function we're going to minimize. That's our area function. And that's 580 plus 460.56 over x plus 16x. All right, so when I differentiate that, the derivative constant is 0. This is x to the minus 1. So when I differentiate it, the minus 1 drops in front, and then we have a minus 1 as the exponent, so we subtract 1 from minus 1, we get minus 2, but x to the minus 2 is over x squared. And then the derivative of 16x is 16. So now we're going to find the critical numbers by setting this derivative equal to 0. And then I'm going to solve this equation right here. So when I do that, I'm going to move the 4656 over to the right-hand side, like so. And then I'm going to multiply up by x squared and divide by 16. So it's going to look like I'm just swapping these two here. And then 4656 divided by 16 is 291. And now I'm going to take a square root of both sides. Now I get a plus or minus square root, right? Because if I square minus square root of 291, I'll get positive 291. And if I square positive square root of 291, I'll get 291. But x is greater than 0, so we're going to choose the positive. So I'll get rid of that plus minus. And then I'm going to take that positive square root of 291 and I'm going to substitute into this y equals 388 over x so I can get the y value. So there we go, we get the y value. Now, we're not quite done. We should verify that this does actually give us a minimum. So I'll do that using the second derivative test. I'll take a second derivative here. So this is x to the minus 2. So minus 2 times minus 4656 is positive 9312. And then this is x to the minus 2. So when I subtract 1 from the minus 2, I get a minus 3. And then x to the minus 3 is 1 over x cubed. And then the derivative of a constant is 0. Now, this second derivative, you notice that I'm going to be plugging in positive values for x. So the second derivative is going to be positive. Actually, I'm not even going to complete that calculation. I just know that when I plug that in, that's going to be a positive number. And if the second derivative is positive, then you're concave up. And so we have a min at that x value. So I've confirmed that this is a minimum, which is, in this language, is the smallest area. Now, we're not done. We only have x and y, but we want to know the dimensions of the poster. The dimensions of the poster include this plus 6 plus 6, the margins, which gives us a plus 12, and the plus 8 plus 8, which gave us the plus 16. So we have to add these 12 to x and 16 to y to finish the problem. So don't forget to do that. So let's move that up there, and let's move the y over there. And then that is our length and width. So you can't forget to add on those margins there. All right, good luck.